Okay, so this is additional note 3. Where I shall discuss Schrodinger representation of QFT. Okay. So what do I mean by Schrodinger representation of QFT? Recall that the way I presented Klein-Gordon theory was exploiting a mathematical analogy with the harmonic oscillator quantization. So we exploited a mathematical analogy between harmonic oscillator and the Klein-Gordon theory. And according to that analogy, the harmonic oscillator operator x of t goes to phi tilde of p t comma p vector. So then various results in the harmonic oscillator side were translated to the quantization of Klein-Gordon. That is how we arrived at. So we didn't have to give independent arguments to quantize Klein-Gordon theory, but rather translated from harmonic oscillator results. Now, so what are the similarities and differences? So we have this position operator that corresponds to this operator. In both the cases, the operators are functions of time. So that is the formulation of non-relativistic quantum mechanics. This one is a single degree of freedom, but here on the QFT side, we have infinite number of degrees of freedom, because for each value of the three-dimensional momentum, this is an independent degree of freedom. Now, one crucial thing that also was used was a correspondence between this state t comma x and phi hat of x acting on vacuum. These two operators are related by Fourier transformation. Now, what I'm going to point out now is that this is not the same mathematical analogy as this one. Rather, this correspondence is a physically motivated one. The reason is that this is a state that corresponds to an excitation at an event, t comma x, and we constructed that state. We argued that phi hat of x acting on vacuum creates the similar state in the QFT side, which is why under a relativistic, in the relativistic context, it is the same state that is given by this one, and using the word line theory, we calculated this propagator. This is using relativistic word line theory, and here we calculated Green's function of time ordered product if phi hat y, phi hat x. Yeah. So it is because of this analogy between this state and this phi hat x acting on vacuum that we had an equality of this between these two. Yeah. So if the so this is the argument, if the word line theory is automatically causal, then that should match with this, and we saw going through some explicit computation that is indeed true. We showed that these two objects are actually same, right? Now here in this entire story, we have never used any mathematical analogy. Like, we did not translate anything. Rather, we gave an independent physical argument to claim that this is the object that should be identified with the state, for which, using word line theory, we calculated this propagator, right? And without an explicit calculation, without the verification using explicit calculation, this is only an intuitive argument, but there's no evidence, direct evidence that that is true. So that equality, when we showed that this is equal to this, it shows that that argument is right, that expectation is right. Okay. Now, if that is the case, then the question would be, what if we had used the same mathematical analogy and applied on this state? What would we get on the QFT side if we had applied the mathematical analogy? So question is, what state in QFT must be the mathematical analog of t comma x vector in non-relativistic quantum mechanics? That is the question that we are going to explore today, and that would lead to what I'm referring to as the Schrodinger representation of quantum field theory. The Schrodinger representation of quantum field theory, though we motivated the question from the particular example of Klein-Gordon theory, but this is a formalism that will be true. The formalism that we will arrive at will be true for any quantum field theory, not for a specific model like Klein-Gordon theory. So let us first, to explore this question, let us first recall the definition. Recall the definition in non-relativistic quantum mechanics, which is this: x hat of t acting on t comma x vector is equal to, this is three-dimensional, is equal to x vector t comma x vector. Now, so since we are asking this question, what is the QFT analog, mathematical analog of this, we should ask what is the QFT generalization or QFT analog of this statement. This, we will just exploit the mathematical connection. So x hat operator is replaced by phi hat t comma p acting on t. Let me introduce the notation first, and then I will explain what it means. Should be equal to phi tilde of p t comma phi tilde. You see, when you read out this equation, what it says is that the state has a label which gives you the eigenvalue of this operator. Okay, so here also we have a label here for the state which must give the eigenvalue of this operator, and that's this eigenvalue at a particular time t, when as long as we take the same time both in the operator and the state. Now, since this operator, there are an infinite number of them, there's an independent operator for each value of p, the entire information. So that means this label must know for all possible values phi tilde for all possible values of p vector. That means this must be encoding the entire functional form phi tilde p. So this encodes the entire functional form phi tilde of p. Now we know that from here, using this definition and the position and corresponding conjugate momentum equal time commutator, we can arrive at the position space representation of all operators, and that's the Schrodinger description of non-relativistic quantum mechanics. So this gives you position space representation of all operators, and that gives you Schrodinger description of non-relativistic quantum mechanics. Similarly, here in this case, we cannot say it's position space. So what is position here, or in this non-relativistic quantum mechanics, has become phi tilde of p. So we may call it phi tilde p representation, or position space representation, provided we understand what we are referring to. Of operators, and that must give us the Schrodinger description of QFT. Right? Now, given these states, having introduced these states and defined through this relation, we can now talk about, so these are like bases, just like these were basis states in non-relativistic quantum mechanics. These are also basis states in the quantum field theory that we are considering. So you can talk about orthonormalization, and completeness of these basis states. Orthonormalization will be given by t comma phi tilde t comma phi tilde prime, given by Dirac delta of phi tilde minus phi tilde prime. Now this is a functional delta function, the functional delta function, which imposes equality of two functions over the complete range of their domain. One formal description would be of this would be, say, product over P delta phi tilde P minus phi tilde prime P. This is just like in the path integral measure can be viewed as product of over each point in the domain on which the function is defined, on which the path is defined. So we already encountered this kind of this kind of ideas. But this is a very formal description of this quantity. And so I should basically, I think I should clarify here, this should be mentioned here, that this Schrodinger representation of quantum field theory is a formal description that we are considering here, is a formal description. However, this can be made well defined through discretization. Or lattice construction. This is similar to the time slicing. So when we introduced path integral, we considered paths or functions for which the domain is some interval in the time, and we slice that time interval into n portions, in equally spaced intervals, and then finally at the end of the calculation took n going to infinity limit, and the spacing, which is epsilon, going to 0 limit, such that n times epsilon remains finite. Now this is a one-dimensional latticization. When you describe things on the lattice, everything is fine. They make sense, because in that case, this path integral measure is just a product of the ordinary integration measure at each lattice site, at each point, discrete point here, right? So here, similarly here, we should consider latticization of the momentum space, the entire momentum space, this P space. It's a hard dimensional latticization. It's a three-dimensional lattice, and then these P vector will belong to some discrete points in this three-dimensional space, and therefore this product makes sense. And this is how you can make this well defined. And if you calculate any physically relevant result, then you can do the calculation for the lattice, and then finally take the continuum limit, which is taking this lattice spacing going to 0 and the number of lattice points to infinity. So it is in that spirit we will write for certain formal expressions. The goal or the motivation for writing down those formal expressions is to lay down the conceptual, is to clarify the conceptual side, so that can guide when you perform the latticization to make it more rigorous. Before you define the things on lattice, you need to have an idea of what you are doing. Since we are not good, so that lattice construction is a more sophisticated calculation, which we will not perform here, will not do it here in detail, but it is in that spirit that we should consider such formal expressions. So all the expressions that I will be writing down in this discussion should be taken in that spirit. In case you want to do it rigorously, you laticize and follow the similar construction there. Okay, that is the idea. So viewed from that perspective, this product over P is it makes sense, because then it's just a product of a large number of delta functions for each discrete value of P. And therefore you could also write this as integral path integral, say kappa times exponential I integral dn P kappa P times phi tilde p minus phi tilde prime p. So what it means is that for each value of p, I have an ordinary Dirac delta function minus phi tilde prime, and that Dirac delta function can be written as integral dk. So you could view this also formally as product over p d kappa p over 2 pi to the power n. So for each discrete value of p, we have an ordinary integral d kappa over 2 pi to the power n e to the power I kappa times phi tilde minus phi tilde prime. And then you take a product over all possible discrete values of p, and then exponential, it's a product of exponentials. So in the exponent, it becomes a summation, which is why I have an integral over p. Okay, so so this is how one could interpret this delta function, and the completeness can be written as integral d phi tilde t comma phi tilde is equal to identity. I think this is now, I have explained everything, so I don't have to explain it any further. Then you can write down wave functional. So for an arbitrary state, so for an arbitrary state, say psi, I mean in QFT, you could write psi equals integral d phi tilde okay, phi tilde so now onwards I will be fixing the time. So now onwards, fixed time. And all the equations that I'll be writing is for fixed time. So I will not write this. I will not write this t explicitly in all equations. And this is the wave function. So wave function null. So phi tilde psi phi tilde. This is a wave functional for the state psi. Now, as I said, that we can construct all the operators in QFT in this quote unquote position space representation, and that comes from not only this equation but also from the equal time commutation relations. So what is the equal time commutation relations? That is known in the position space of the field. So consider position space field operator. That phi of x is related to, as I mentioned here, is related to this one, which is the analog of x hat through Fourier transformation. So I'm writing down that same Fourier transformation equation. It's given by d n p over 2 pi to the power n by 2 phi tilde hat t comma p vector e to the I p dot x. And phi hat of x is equal to integral dnp over 2 pi to the power n by 2 phi tilde t comma p e to the I p dot x. Okay, so this is the conjugate momentum. So the construction is going in this following manner. We have x hat of t in non-relativistic quantum mechanics. Corresponding to that, we have phi tilde of p. That from the phi tilde of p, we are starting from phi tilde of p because that is how we can. It is for that one we can directly write down the analogs from harmonic oscillator, because this is the analog of x hat operator in non-relativistic quantum mechanics. Now I have to go to the equal time commutation relation. So from here I should first go to the position space field, and then from there it is the conjugate momentum from phi hat. If I have the theory, the Lagrangian, I can calculate what pi hat is, and then pi hat has to be Fourier transformed, and that is pi tilde of p. Now, now equal time commutation relations. Equal time commutator is phi hat t comma x pi hat t comma y is equal to I h bar delta x minus y, and from here show that we must have between phi tilde t comma p and pi tilde t comma q the commutation relation I h bar delta p plus q. Therefore, the point here is that in the momentum representation, the conjugate momentum corresponding to phi tilde of p is pi tilde of minus p, because it is the delta function p plus q. Okay, so that's going to be important.